Okay, welcome everyone to my continuation of what is category theory. Today, a lot of diagrams, hooray. So what are string diagrams for monoidal categories? So take two if you want. So for monoidal categories, string diagrams get a little bit nicer. And for enriched categories that are even beyond monoidal categories, they get even nicer. I'll just sketch that for now today. And then later we go to, well, more quantum algebra type categories. We'll see. But even today, we'll see already a two-dimensional calculus, the one I promised all the time. So monoidal categories are actually two-dimensional in contrast to kind of the one-dimensional algebra we all learn in school, like multiplying numbers or whatever. So monoidal categories is like a two-dimensional calculus. So to get us all on the same page, let me recall string diagrams. String diagrams, really cool concept to kind of visualize what's going on in categories. I use that, for example, for the kind of the definition, if you want, or the visual picture of an adjoint functor. But here you go. It's more general, actually. Just let's recall it. So usually you would like to draw a category as a face. So some coloring here, kind of fun that everything turns around. So the zero-dimensional thing becomes two-dimensional and so on. And the two-dimensional thing becomes zero-dimensional anyway. So you would draw a natural transformation as a point or as a little coupon on my little diagrams here. So here's my little coupon. And you would draw a functor as a line. Standard calculus here, you stack everything together, or you can use your kind of diagrammatic intuition to manipulate those diagrams. And it just reflects, it's just a really good way of writing algebraic manipulations of diagrams, of arrows or whatever, of functors in terms of diagrams. It's really, really nice and kind of really cool way of doing it. Kind of a very conceptually clear, if you want, way of thinking about manipulations of functors. It's pretty cool. And for monoidal categories, it looks like this. So kind of get rid of the face colors. I won't explain today why, because it gets beyond the material I wanted to cover today. But let's just say it is the way it is. So you don't need any face colors. There's some kind of a fixed color if you want. I could color my background with a fixed color if I wanted to. But of course, it's a fixed color. If I just can choose my fixed color, I take white, so you can't see it. So there is no face coloring needed. But otherwise, I do exactly the same. I draw an object now as a line, an object here, or this would be, strictly speaking, the identity morphism on that object if you want. But anyway, that's kind of the same. You can identify the identity morphism on an object with the object, of course. And I would like to draw now my arrow, so my morphism here, as a little coupon. So this goes from X to Y, so I'm reading kind of in this direction, but actually my reading conventions don't matter so much. So this is a little coupon here going from the object X, which is a little line, to the object Y, which is the other little line, and it's just this coupon type picture, and I call this string diagram for monoidal categories. Okay, sure, fine, but now I need to explain to you how to read those diagrams. Actually, these are just the local pictures, and the point is two-dimensional calculus. So composition, we have two ways of composing the pictures. They really naturally come up from this way of thinking about arrows in this case. So you can compose arrows, the usual composition of arrows, by just taking this picture, and you stack them on top of one another. And let me try to give this a color here. So this is the one on top, and you end up with a picture that looks like this, right? Now, this one here is glued to this part, so you get this little picture from X to Y to Z, and of course you can just say this is a morphism FG. So composition of arrows is just stacking vertically, right? It's a vertical stacking of diagrams. Okay, that's pretty nice. Okay, we can stack them vertically on top of one another, whenever that makes sense, of course. But it's the same for composition. Anyway, you can compose only arrows whenever it makes sense, right? Whenever whatever it is, the target of one is the source of the other, or something like that. You know how to compose arrows. But obviously, we are living in a plane here. So, well, not obviously, but we are living in a plane. Well, I'm certainly living in a plane. I'm certainly not living in a plane. We are living in 3 space. But my picture here is certainly in a plane. And in the plane, I have a certain different operation. I can not just stack vertically, which is kind of this part, but I can stack horizontally. And this is now the monoidal structure. Kind of the first point, it works in any category. So you can use string diagrams for any category. They lose a little bit of interesting flavor. They interest because they're just, it's still one-dimensional because it's just stacked vertically. You just draw them in a different way. But now we can actually stick diagrams horizontally. So So you can take your diagram here, you take your diagram here, and you just put them next to one another. Let me give one of them again a color. So here's this little color, and you just put them next to one another, and you get a new diagram. And this is just a horizontal composition, the tensor product in this case of f and g. And there's a nice, really nice picture here. So the usual kind of, this is called the interchange law. So one of the laws that you need for monoidal categories actually is just encoded by height move, right? They're unrelated, they're very far apart. So I can move the coupons, I can move G down, F up, or F up or G down or something, and you just can move them past one another. It's a very nice way of thinking about it. And I really have a two-dimensional calculus now where I can stick pictures left to right, I can stick pictures bottom to top, I can slide things around, and this just encodes in general monoidal category, which is kind of a really cool way. I personally think it's a really cool way of thinking about monoidal categories. And this really is the gets here. So string diagrams for monoidal categories have, I can't explain that right now. We'll see later what actually question mark is as a portion of the plane, right? My white background that I'm not even drawing anymore. Objects are strings and arrows are coupons, and the evident composition rule. So here, the prototypical example where this is all modeled on is my favorite category, or one of my favorite categories. I'm not quite sure. Vector space is also very nice. One of my favorite categories is the cumbersome category, where, for example, the tensor product is just the tensor product I just explained. Not to get confused here, strictly speaking, each line here represents an object, and whenever I draw this picture in the cumbersome category, it actually should be this picture with a little coupon, but you kind of ignore the coupon because there's just one arrow in this case, and you just define the cup or cap or whatever it is as the picture with the coupon. So I'm erasing a lot of coupons here in this picture, and there's also this map here, which secretly is kind of a coupon like this. And I just get rid of the coupon altogether. Just not to get confused, but this is really a monoidal category. This is really a string diagram category in the sense I've showed you on this slide, or on this slide, depends a little bit how you would like to do it. But I just erase the coupons because it's kind of the trivial case, if you want. Anyway, so the big theorem here is the two diagrams here really. You can do now manipulations in monoidal categories using those diagrams. And two diagrams are related by scaling, or scaling, you can always scale them as much as you want, or by planar isotopies that kind of keeps the upwards orientation. So it's not quite all planar isotopies. So what's kind of missing is the move that I showed you from for adjoint functors in a slightly different setup. But the zigzag move, it's kind of missing. So it's not quite a two-dimensional calculus. You're missing a little bit because everything should be somehow upwards oriented. Whatever kind you can do on upwards oriented things, so like the height move or whatever, that's fine. But you're not allowed to do some kind of Morse type moves. You don't want some kind of points where you have some horizontal tangent lines. You don't want that. You can't do that in general. So it's not quite two-dimensional calculus. I was lying a little bit. It's still a little bit. It's still two-dimensional in nature, but it's not completely planar. And kind of missing the fill-in point here would be quantum algebra, which we discuss later on. So we can actually beef it up a little bit, make it really planar. But for now, just the theorem that we have is that two morphisms, so two diagrams, are equivalent. So they represent the same arrow, they represent the same morphism, if and only if, kind of nice, they are related by some scaling or planar isotopies that keep the upwards orientation, right? So it's kind of a cool theorem. It's not so hard to prove, but it's kind of cool. And it basically says, now you can do any kind of manipulation you want in the monoidal category. You can replace it by kind of diagram argument in the plane. So it really is, well, maybe not really, but it is kind of a two-dimensional calculus. And the not really here is that somehow the height move operation, or sorry, not the height move, the zigzag operation is missing, and you kind of need to build that in by enriching your categories a little bit further, which I'm going to explain in a later video. Anyway, string diagrams, I hope you really like them. They're pretty cool. It's a cool way of thinking about categories in general, and monoidal categories in particular. It gets two-dimensional. You have your little coupons everywhere. You can move them around. It's a pretty cool concept to think about categories. It's really rigorous, by the way. It's not like you draw a diagram and you explain things on a diagram where you're not allowed to do it. No. It's just instead of writing algebraic symbols, if you want, you write diagrammatic symbols. You can do exactly the same rigorous arguments just using your visual intuition, which is the whole point. Anyway, I really hope you liked string diagrams. I hope you enjoyed the video, and I also hope to see you next time.